in 2020 and then have joined as an assistant professor in this college. So thank you for giving me the opportunity to present our work here in this refresher course come summer school program. So okay, so today I'm going to uh, uh, present on a talk on coupling of waves in the solar atmosphere. So before going to the details of my work, so here are some brief introduction on our solar atmosphere or on our sun. The next slide. Santosh, uh, next slide. Yes. So this is our sun. So, but right now I cannot point. I use the pointer because the screen is shared by Santosh. So this is our sun in from space in different wavelengths. If I go to the top panel, top left panel, like AIA 1700. So this is something that how the sun looks from our Earth, right? It looks like a plain yellow ball. It's calm. But if you go to space and if you take images at different wavelengths, like here I am showing, you can see at the top of each panel, I am writing AIA 1700 angstrom, AIA 1600, AIA 304 angstrom. Actually, these are some of the wavelengths taken by an instrument AIA, Atmospheric Imaging Assembly, on board this satellite SDO, Solar Dynamic Observatory. So if we got, and this wavelengths corresponds to like a far UV or extreme UV or near UV, like different wavelengths. So now this different wavelength, actually what happened, they correspond to different temperatures. So hence different layers of solar atmosphere with height. So this is not, our sun is not like a plain yellow ball that we see from our Earth. It is very dynamic. It's full with many activities. And this is how it looks from the space in UV or extreme UV. So next slide. So if anyone has any problem in understanding because I am not able to use my pointer, so please let me know or ask me immediately. So see, this is our sun taken by the same instrument AIA onboard SDO, like Solar Dynamic Observatory today. This is our sun today. It was today morning. This image was taken by this satellite. So if you see, this is not like here in Assam. I'm from Assam. This is like even I can't see the sun. It's cloudy. But this is how it's full of many activities. We can see many structures here. These are called fan loops. These are actually magnetic field lines. So they are confining the plasma. That's why they are look bright. And these are also known as active regions. So there are, if you see the whole sun, there are some bright regions like which we call active regions. There are some dark patches like which we call as like coronal holes, and the rest of the sun is we call quiet sun. So next slide. Okay. So yes, this is when we say our sun, it's mainly divided into main two parts. One is the solar interior, which we cannot see, and one is the solar atmosphere, like again, which we cannot see with our naked eye. What we see from Earth, it is just the surface of the sun. So if we go to the solar interior, like you can see in the image, the first part is the core. We call the solar core, where the whole fusion reaction happens and giving rise to enormous amount of energy. So where hydrogen fused to give rise to helium. Then whatever energy is getting generated in the core, that comes out, so that travels outward through different processes. Like just outside the core, there is a zone called radiative zone. In the radiative zone, what happens? The mode of energy transfer from the core is a radiation method. This is a radiation process. So this radiative zone is pretty big. It is like 70% of the total solar volume, solar radius. Then just after the radiative zone, so there is a called convective zone where the mode of energy transfer from the radiative zone to the convective zone is a convection. Like we all are aware of the method of convection. There are three main process of energy transfer. Like we all know radiation, like we get heat from the space, like from the sun to our Earth. There is vacuum in between. Like still we get heat. So this is the method of the process of energy transfer is radiation. Then there is conduction. Conduction is the method of energy transfer in metals, like or in anything, like by the vibration or collisions of these atoms and molecules. And finally, we have the convection we all are aware of, like the bubbling of water. When we heat water, the hot water rises up and the cold water goes down. So it's the bubbling of water, that is the convection zone. So the same thing happens inside the solar interior also. First, we have the core where the heat gets generated. Then the heat travels outward to the method of to the process of radiation, and finally the convection. So this is, and once after the convection comes the solar surface that we see from our Earth, that which we call as the solar photosphere. Like whatever we see from Earth, that is called the photosphere or the solar surface. So from the solar surface, the solar atmosphere starts. So first is the solar photosphere. So we all know. So in the right hand side, I am showing some images. If you see from the bottom, photosphere, chromosphere, corona. Okay. Actually, this photosphere, though I am showing in like in black and white color, actually this is how from Earth our sun looks, the solar surface looks. So this is the photosphere, which is around 5050 which is around 550 kilometer thick, and it has a temperature of around 6000 Kelvin. Then just after the photosphere, there is a layer atmosphere. Again, all these things we cannot see from with our naked eye. Like chromosphere is around 2000 kilometer. Then we have a very thin region called transition regions, which is around 100-kilometer thick, and all those dynamic activities happens here. And finally, we have the outermost atmosphere, the corona. So if you see on the right, like from the photosphere is very calm, then chromosphere, and as we go up the corona, I'm showing it in two wavelengths. At one is in AIA 171, one is in AIA 211. So means different wavelengths means again at different temperatures. So I'm increasing the temperatures actually with height. Okay, so this is what our solar atmosphere is. So next slide. Okay, now here arises one problem. So as we know, the heat, as we heat travels outward, as heat travels outward, as it comes outside, generally temperature should decrease. So the same thing happens in the core. The heat is getting heat generates. It comes to the photosphere and finally to the atmosphere. So in the photosphere, the temperature of the surface photosphere is around 5000 Kelvin. Then with height, it slowly decreases and gets a temperature minimum region of around 4000 Kelvin. But after the temperature minimum region, sorry, is it okay? I'm not able to use my pointer. Is everyone is getting what I'm okay? So this is a diagram of height versus x-axis is height, like solar atmospheric height, and y-axis is the temperature. So I am means from left, I am going from the solar atmosphere, solar photosphere to outward direction to the corona. So from photosphere, as we goes out, the temperature slowly decrease. This is fine. The temperature is decreasing with height. Then we are reaching a temperature minimum region, but then it slowly starts to increase in the chromosphere and reaches around 20,000 Kelvin. Now here the things happens. Say here in the this is the reason when it reaches 20,000 Kelvin. So just after that there is a thin layer of around 100 kilometer in thickness. So here the temperature suddenly abruptly rises to around 0.8 million Kelvin or million Kelvin and reaches the corona, the outer atmosphere of the sun, which is in million Kelvin. So there is a within a very thin region the temperature suddenly increases from low to high with height. So which is against the law of thermodynamics because temperatures should decrease with height, but which is not happening here. And this is one of the unsolved problems in coronal in solar physics, which is known as the coronal heating problem. And here in the there is one small panel. So here I am showing the solar corona. Solar corona. So generally solar corona we cannot see with our naked eye, but during eclipse, like this is an eclipse, our when our sun is obstructed by the moon or something, in that time only we can see the faint coronal we can see the very faint corona. but but here we see that the corona is not very simple. It's there is magnetic field lines, so it is very structural actually. And here the temperature rises to a million Kelvin. So next slide. So, as I have told, so this is one of the unsolved problems in solar physics, why the corona is so hot. So, there are many mechanisms so far have been put forwarded to explain this coronal heating. One is called this nanoflare heating, which I'm not including yet. This is like the magnetic reconnection of these magnetic field lines. As we know, the sun is full with magnetic field lines. And another one is wave heating, which we call as magnetohydrodynamic wave heating. Actually, these waves which are getting generated in the lower atmosphere, they are going up and they are dissipating their energy, contributing to the coronal heating. So now the question comes how these waves are getting generated in the solar atmosphere. And the simple answer we generally know, this is a convective motion. So we know below the photosphere means the solar surface, we have the convective zone where the whole convection, like bubbling of solar plasma happens. And this whole bubbling of solar plasma, this is a very turbulent process. It gives rise to the different wave modes, which and these waves they travel outward and dissipate their energy. And recently in last like 1-2 decades with the advent of technology, so we have been able to observe these wave modes in different solar structures. Like the sun is very huge, it is full of many different dynamic structures, which is, and I'm not, it is not possible to show the observation of waves in all those structures. So here I'm showing just a few structures where we can see the presence of waves. The first one, let's start from the photosphere. Okay, here on the right, you can see a panel, like yellow panel. Like here you can see there are small bubbles. Like below there is a dark black spot, but surrounding it, there are some white bubbles. So these are called granules, and these are the results of the convection. So convection, what happens when the hot plasma they goes and they comes up and they appear bright, and the cold plasma they goes down to the surrounding region, then they appear bright. The whole solar photosphere, means the solar surface, is full with such granular or this bubbling pattern. So, and these bubbles they are not steady. They are in constant motions all the time. And these granules are also in this convective motions also. Again, it's giving rise to the different wave modes. So this is in the photosphere. Then here I am showing in the bottom panels some structures. I am showing some bright this actually magnetic lines. So these are actually called fan loops. So these fan loops are they are some magnetic lines. They have a temperatures of less than 1 million Kelvin, and they appear bright as a confined plasma. So and they're open field lines. We call them as fan loops. They are observed in the solar outer atmosphere, means in the corona. So we have observed propagation of waves along this fan loops also. So here, just near this fan loop, there is another image. So here we can see like some propagation of which time, y-axis is the time. So there is some propagation of this intensity variation. Intensity, some brightness, some darkness, some brightness, some darkness. Actually, these are some waves only. So generally what happens in the next slide, next few slides, I'm going to speak about this. So this is a kind of waves which we know call as slow magnetoacoustic waves. Acoustic means sound, like whatever property sound show, such kind of property these waves also show. Like why do sound arise? This is the propagation of pressure. Means propagation of compression of pressure means propagation of density. There is compression, density increase, then rarefaction. There's a decrease in density. So compression, rarefaction. And whenever there is an increase in density, so increase in intensity, then we see all these brightenings. Then when there is rarefaction, there is decrease in intensity. Then we see all this, that means dark ridges. This is how this intensity enhancement or density these perturbations they propagate, and we can measure the propagating speed of these intensity disturbances, and we have found that that is means below 150 kilometer per second. Generally, as we know, like in art, the velocity of sound is around 332 meter per second. But in the solar atmosphere, the temperature is high. We know the velocity depends on the formula is gamma p by rho or gamma RT by rho. So it depends on temperatures, right? So here in the solar atmosphere, if you consider 1 million Kelvin, the temperature is below 150 this 150 kilometer per second. We have got that velocity, means there the whatever propagating disturbances we are observing in the solar atmosphere, their velocity is comparable to the acoustic wave in the solar atmosphere. So we call them slow magneto-acoustic waves. Next slide. Okay, then question comes, how do we observe those waves? Obviously, as I have said, like in the earlier slide, I showed you one image, like where these propagating intensity disturbances were there. So one is means the imaging observation. We go to space, we have this all this spacecraft, and they take images. So from those images, by using some techniques, we can catch those density variation or intensity variation, or we can say that the wave is propagating. So one is that imaging observation, and second is spectroscopic observation. Like some waves show, like which we call as compressional waves. They cause those intensity perturbations. Means they show variation in intensity. But there are some waves, even when they propagate, they don't show any intensity variations. So those waves are very difficult to detect by imaging observations. For that, we have to go to spectroscopic observation, but it is a completely different, like some techniques. So I'm not going into the details of image spectroscopic observation in this talk. My whole this talk will be confined to imaging observations only. And so far, there are different missions are like there, like Hinode from Japan, SDO from NASA, IRIS, NASA, Solar Probe. Recently, it has been launched, then Solar Orbiter. And next year, India is going to launch its first solar dedicated missions, Aditya L1. So we are going to have a lot of data. So we need just people. So if people are motivated, you're always welcome. Okay. So next slide. Okay. So question comes, what is the nature of these waves that we observe in the solar atmosphere? See, generally the whole sun is plasma, it's fluid, right? So the nature of the waves will be hydrodynamic. But this is not just plasma embedded in magnetic field. So it will be magnetohydrodynamic in nature. So there are a few MHD equations. So I'm not showing all those equations here, because otherwise it will be complicated. So once we solve those equations, basically we get three wave modes. One is the L1 wave modes. Second is the slow magnetoacoustic waves, which I have I have shown. And finally comes the fast magnetoacoustic waves. Now, this L1 waves, the first mode and the third mode, fast magnetoacoustic waves. Those waves, in my study, I have not considered L1 and fast magnetoacoustic waves. I have only considered slow magnetoacoustic waves. And slow magnetoacoustic waves, they are compressional. As I have said, compressional means they show variation in intensity. Okay, means there is compression rarefaction, uh, there is means change in density, or there is change in intensity. That's why they are compressional, and their nature is longitudinal. We all know about longitudinal waves and transverse waves. Then again, just I'm saying one line, this L1 waves, this is a bit different waves. It is incompressible, means these waves when they propagate, they don't show intensity variation. As a result, it is very difficult to detect the propagation of L1 waves. And to detect L1 waves, we have to go to spectroscopic observations. And these L1 waves are transverse in nature. We all know about transverse waves. And finally, we have the fast magnetoacoustic waves. They are compressional, means like they show intensity variation, and they are again longitudinal waves, like slow waves only. But thing is, their velocity is very high. It's more than it's 1000 kilometer per second. That's why they are called fast magnetoacoustic waves. Next slide. Okay. So again, the wave study of waves in the solar atmosphere itself is a huge topic. So it is not possible to tell about all those waves. So I'm confining my study to those waves observed in the sunspot atmosphere. So what is sunspot waves before going there? So let's see what is sunspot. So here you can see in the top panel, you can see and structures. The center of the structure is very dark, surrounded by a less dark surrounding. Okay, so this is called sunspot. The sunspot are some structures. Uh, Actually, these are some structures where magnetic field strength is very high, that runs from 2000 to 3000 Gauss. So what happens? So these are the regions of very strong magnetic field, and these magnetic field lines, they inhibit the convection. Like we know the convection keeps happening all the time, and whenever there is an there are many field lines, they inhibit the convections, they inhibit the convections. As a result, heat cannot come up effectively to the outer atmosphere, and as a result, the temperature of these regions become lower than the surrounding regions. That's why they look appear darker as compared to the surrounding regions. And this sunspot, they are generally, it has two main parts. The central part is called umbra, where magnetic field lines are vertical and surrounded by these less darker regions, which is known as penumbra. In penumbra, the magnetic field lines, they spread out. Now, what happens? This sunspot also, if we study it properly, this sunspot also shows some inherent oscillations, and we know whenever there is oscillation it should give rise to some waves. Now when we see the sunspot, this is how it looks in the lower solar atmosphere. Lower solar atmosphere means solar surface, means solar photosphere. See here we can see some black spots in the bottom panel. Then as we go up, so we photosphere, then comes chromosphere, finally corona. So we can see it appear different. Actually, these are the same sunspot, but here it appear different because the strong field lines associated with those sunspot, they confine plasma and they appear bright. So we can see that the same sunspot appear different in different layers of the solar atmosphere. Now, what happens? This sunspot, as I have said, they also show some inherent oscillations and propagations of waves. If we study those sunspot in the photosphere, generally we can see some oscillations which have a period of around 5 minutes. Then as we go up and we reaches the chromosphere, the oscillations associated with the chromospheric sunspot, it becomes it periods becomes 3 minutes. And again, there are some waves in the chromosphere also. So the velocity of those waves are again different from the photospheric counterpart. And then there are some oscillations called umbral flash oscillations. I'm coming. So umbral flash oscillations are some brightness, like the sunspot umbra. This center part is always dark, but sometimes some brightening happens, and they have a periodicity of around 2 to 3 minutes. So those brightenings, which happen with a periodicity of 2 to 3 minutes, they are known as umbral flash oscillations. Then this is the sunspot. If we look at it radially, like from the umbra to penumbra, if we go from the radially outward, if we look at it, we have this running umbral and penumbral waves. We can see some propagations of umbral waves, then some penumbral waves, means radially outward. And finally, we have those coronal waves, the same sunspot in the corona. So along these structures, these magnetic field lines also, we can see some propagation of waves, and they are known as coronal waves. And it has been found that all these waves, they have different properties. No doubt they are slow magnetoacoustics, but their periodicity is different, their velocity is different, many things are different. So we don't know whether this is the same wave is propagating up, or it is their origin is different. So as we know, wave study is important because by studying those waves, we can indirectly know about the medium along which these waves propagates. So if we can see, find that this, yes, these waves are connected somehow. So we can all again say, imply that the solar atmosphere is also somehow connected. So that's why we do all these studies. And again, one of the reasons, as I have told, to understand the coronal heating. So we have to characterize these waves, means we have to measure its properties. We have to then calculate the how much energy these waves can carry. And finally, we see whether this energy is enough to explain the coronal heating, means higher temperature of the corona. Next slide. Okay, so as I have said, so the objective of our study is to study the different sunspot waves observed in different layers of the solar atmosphere and to understand their coupling. Next slide. Okay, so this is what our analyzed active regions is there. So I am sure this whole study is done by so atmospheric imaging assembly on board the Solar Dynamic Observatory. So AIA is an instrument, it's a payload on the spacecraft Solar Dynamic Observatory. So the whole sunspot analyzed regions I'm showing here in different wavelengths. Again, I'm showing different wavelengths means different temperatures or different layers of the solar atmosphere. So you can see on the top panels like top HMI Continuum, AIA 1600, AIA 1700. Here we can see the sunspot. There is umbra, middle darker part surrounded by this penumbral part. But as we go upward, as we go to the means corona, the sunspot disappear and it appear in the form of fan loops. These loops we can see. Fan loops means, because as I have said, actually these are sunspot are regions of strong magnetic field lines. So these field lines appear in the solar corona. So here the photospheric lower atmospheric counterpart of sunspot, and this middle and the bottom panel is the upper atmospheric counterpart of the sunspot. Then again, but here I can in the bottom panel, in the there is one panel called HMI magnetogram. This is again a different image. It will give you the polarity of the sunspot, whether it's positive polarity or negative polarity. It's a different thing. So the whole study, the data is taken for 45 minutes, like not 9:30 to 10:15. It was 11 December 2010 data. Next slide. Okay. So as I have said, so in this study, I'm going to study the sunspot waves and oscillations. Sunspot waves and oscillations means one is those umbral flashes, like umbral flashes in the upper panel I am showing. These brightenings happening, you see, there are few brightenings happening in the sunspot umbra. These are called umbral flash oscillations, and they have a periodicity of 2 to 3 minutes. Then there is chromospheric, and these umbral flashes are lower atmospheric phenomena. They happen in the photosphere or chromosphere. Again, in the photosphere and chromosphere, there are some radially propagating means waves called umbral waves also. Umbral waves, they propagate along the along the umbra to the outer sunspot area. And finally, in the coronal counterpart, means upper atmospheric part of the sunspot, we have this fill lines and we have this coronal waves. So in this study, basically, we are trying to study umbral flashes oscillations, umbral waves, and this upper atmospheric coronal waves. Mainly, we are trying to study whether the presence of one oscillations or one wave mode affect the propagation of the other wave mode. That was our objective in this study. So during our study, as I have said, we observed 5 bright flashes between 9:46 to 9:57. So during this time, so we detected 5 these flashes. Now these flashes are some very strong brightening. If we see its light curves means variation of intensity with distance. They are very sharp. Okay, they are very strong brightenings. So we want to see these brightenings, they are happening in the lower atmosphere, whether these brightenings are affecting the propagation of other wave modes. Means other wave mode means umbral waves and the upward propagating coronal waves. And to study those waves, we use a technique called time distance analysis technique. So this is some, because in research we have to use different techniques to extract the informations. Like a satellite gives you the data in the form of like images or in the form of, again, spectroscopic data, but we have to use, the more techniques you know, the more things, information you can extract. So it all so most of many of the things in research is depends on how much techniques you know. So time distance analysis in one is one such techniques to extract the wave informations. So time distance, so to in this technique what we do, we use an artificial slit. Here you can see some bend, this curve, right? So this is an artificial slit. I am drawing this in such a way so that it crosses the umbral flashes in the lower panels. You check umbral flashes. It also goes through the umbra, is going through the umbra, as well as it is tracing one pen loop also. You see the middle panel, the lower middle panel, AIA 171. We can see this uh, this slit. It is tracing one fan loop also. So means it is going through the flash, it is going through the sunspot umbra, and it is going through the fan loop. So means it is going to catch three oscillations and waves. One is the umbral flash oscillation, one is umbral waves, and one is coronal waves. Next slide. Okay, and this is how the time distance maps, the results of the time distance analysis appear. So in the upper panel, just see there are four panels. The x-axis is the time and y-axis is the distance. So this is called time x distance analysis. So now the upper panel, AIA 1700 and 1600, these are some wavelength channels which correspond to lower solar atmosphere. Lower solar means basically photosphere and chromosphere. Then the bottom panels, AIA 171 and AIA 211, there are some wavelengths which correspond to upper solar atmosphere, means corona. So now I'm going to the AIA 1700 or 1600, wherever we go. So I'm just starting, I'm sticking to AIA 1700. So what we can see, there are some with time, it means with x-axis, there is some propagation of this intensity disturbances. Propagation of intensity disturbances means we can see the propagation of bright and dark ridges with time. Okay, and here we can see around when in the time around 9:42 between 10. This is the time when these umbral flashes were happening. So we can see in the upper panels, like when between 9:40 to 10, there is an increase in brightness. I'm not able to use my pointer, so I hope you are able to get it. So actually, like see, so means this time distance map, it is catching those umbral flash oscillations. So I am marking them with this yellow dotted line. I am marking those umbral flash. Okay, and whenever these flashes are happening, there is some propagation of umbral waves also on both sides of the umbral flash. You see the upper two panels, AI 1700 and 1600. There are waves propagating on both sides of the umbral flash, like a fishbone. It's like a fishbone. It's called also a fishbone-like structures. So these are actually umbral waves which are propagating radially outward. And finally, at the bottom panels, AIA 17171 and AIA 211, again there are some propagation of intensity, and but this time they are not both sided, they are just one sided, means these are the coronal waves, they are propagating up along those fill lines. So this is what we our this time distance analysis technique it catch. And what one peculiar things happen here, if you notice, so whenever these flashes are happening between 9 like 47 to 10, simultaneously there is an increase in the brightness of these umbral waves as well as the coronal waves. To observe it more clearly, so we have combined one AIA 1600 image with an AIA 171 image. So AIA 1600 means lower atmosphere and AIA 171 means upper atmosphere. So here we can see these 5 points. There are 5 brightness, 1, 2, 3, 4, 5, the lower panel. So means whenever these brightenings are happening, those 5 flashes are happening, simultaneously there is an increase in the intensity of the umbral waves, and as well as there is an increase in the brightness of the coronal waves also. There is a small time difference, no doubt, because waves will always take some time to travel up. So that's why some time difference is there, but it is happening almost simultaneously. So we can indirectly say that maybe these umbral flashes are affecting, because they are very strong oscillations. They are affecting the propagation of umbral waves, which are propagating in the lower solar atmosphere, and they are affecting the propagation of all those umbral waves also. And I have said here observation of slow magnetoacoustic waves means these intensity disturbances. They are also, as I have said, they are generally, their nature is slow magnetoacoustic in nature. Next slide. Okay. So now to confirm, like whatever we have observed, like they are happening, all these oscillations are happening almost simultaneously. We have to verify it. So what we did to verify, we have done we have taken one analysis called wavelet analysis. I'll come what is wavelet analysis. Just before that, in terms of light curve, I want to show what is this umbral flash oscillations. So you can see in the left panel this UF in AIS 1700 angstrom. Means this is a photospheric lower atmospheric channels. So this is the light curve. The upper panel is called the light curve. Means it is intensity y-axis versus time, and we can see how this intensity is it's changing with time. Now when these flashes are happening during this time around from 15 to 30 minutes, okay, so we can say there is a sudden sharp increase in the intensity. Actually this is the time when those flashes were happening. Now in the bottom panel I have shown this is the top means top left bottom panel, just below the for the UF in AIS 1700 angstrom. There is one yellow panel. We call that as wavelet panel. So x-axis is the time, y-axis is the period. So I'm sure more of you, many of you are familiar with Fourier analysis. Now, what gives Fourier analysis or Fourier gives you? It will give you, I'm giving you a signal. Once you do Fourier analysis on it, it will give you what frequency components are present in the signal. Okay, that is what Fourier analysis gives you. But it will not tell you which frequency component were present at what time. It will not give you the timing informations. So, but if you want to know, so which frequency was present or which period was present at what time, then you have to do wavelet analysis. So this is a this will give you the result is frequency or period versus time. It is going to give you both the informations. So yeah, what we can find here, see, this is when the flashes were happening. First of all, there is some brightening is happening. Like I'm showing it with some contours like blue or black contours. And you see, this is between 20 to 30 minutes. Whenever the flashes are happening, almost simultaneously, there is an increase in the power. And this power, if I extend it to the this axis, this is around 1 to 3 minutes. So period of this power is oscillation is 3 minutes. So wavelet analysis has given you the information. So there is an increase in 3-minute oscillation power between 20 to 30 minutes. So means when these flashes were happening. So on the top of this panel, I am showing you P1 is equal to 2.78 minutes. This means almost near to 3 minutes. So there, when these flashes were happening, there is an increase in wavelet power, or there is an increase in 3-minute oscillation power. So this was happening for umbral flashes in the lower atmosphere. Then I have gone to the umbral waves. So this is umbral waves in AIS 1600 angstrom. So upper panel is the light curve in the light curve. So intensity versus time. So here again we can see, so between 20 to 30 minutes, when the flashes were happening, there is an increase in the intensity or amplitude of these umbral waves also. And if we see the corresponding wavelet wavelet plot, So when in between 20 to 30 minutes, there is an increase in 3 minutes power. Means this is same as the umbral flashes. Then we have gone to coronal waves. So we have selected a channel, AIA 211 angstrom channel. AIA 211 means it's a higher atmospheric coronal temperature channel. So here also in the light curve, we can see. So whenever these flashes were happening between 20 to 30 minutes, there is an enhancement in the amplitude of these coronal waves. And corresponding wavelet plot we can also check. So in between 20 to 30 minutes, so there is an increase in 3 minutes or like around power. So we have found from the wavelet analysis also simultaneous increase of wavelet power around 2.8 minutes, or I'm saying 3 minutes. So 2.8 minutes means somehow all these things the same whenever the flashes are happening, it's affecting the propagation of those umbral waves, which are radially propagating waves, and it is affecting the coronal means outward propagating waves also. Next slide. Okay, so here are some plots which I am means just to get a more clearer picture, means to get a more clearer uh, our pictures. We have to verify our results. Like first we have to analyze, and we have found that maybe this is happening, but just one result is not enough. We have to do it. If we have to check it in many ways. So these panels, these two results, like percentage growth in oscillation amplitudes and cross correlation analysis. So there, with this techniques, I am re-verifying our results. So I'm going to the percentage growth in oscillation amplitude. Percentage growth in means, so there is a background. On top of it, there is an increase in intensity. So I have removed the background, and then I'm checking how much it has changed. How much percentage wise, how much it means how much is the growth. So this is called percentage growth in oscillation amplitude. Again, so here are the bottom panels are for umbral flash, the middle panels are for umbral waves, and the top panels are for coronal waves. So see, and x-axis are the time and y-axis are the percentage means growth in the amplitude of those oscillations. So here again we can see. So whenever these flashes are happening, there's a sudden increase in the brightness, and almost simultaneously there is increase of intensity for those umbral waves also, and for those coronal waves also, means the upper panels. Then in the right image means cross correlation analysis. So we are again trying to cross correlate, means whatever similarities, almost simultaneous increase we are getting, how much they are correlated, whether actually they are mathematically correlated or not. So for that, what we have done, we have taken AIA 1700 angstrom. It's a photospheric channel as the base, and I have correlated the other channels like other waves with respect to AIA 1700 angstrom. And this is the what results we get. The bottom panels are for umbral flash AIA 1600 and 304. Then the middle panels are for umbral waves, and the upper panels are for coronal waves. So now see, whenever these flashes are happening, see AIA 1700 and 1600, they are very near channels. So I can see there is a high correlation. It's near to 1, means y-axis is the cross correlation coefficient. Generally, if we get the correlation coefficient more than 0.5, means they are correlated, and y-axis is the time, means what is the when they are when at what time we are getting the correlation. So umbral phase 1600 and 304, we are getting the correlations above 1. In fact, for the other channels also, if you see, like umbral waves, the correlation is more than 0.5. For this umbral wave 304, correlation coefficient is more than 0.5. In fact, for the coronal waves also. So means we have found they are very well correlated. Second, we find that there is this peak the peak of this correlation coefficient, when it is happening, there is a shift in time. We see, so this is here, this is here, this is here. So there is a shift. Means means the wave is taking time to propagate. It indirectly, that's what it implies, because because these correlations are not happening instantaneously. The waves take some time to propagate along these structures, and that time difference is also getting displayed in the cross correlation analysis. And there are some other plots also in this study which I am not there. They are, those are a bit complicated. That's why I am not showing including those plots in this talk. So yeah, next slide. Just a minute. Okay. So finally, we have come to the conclusions. So in our study, what we have found, first we have found clear propagation of different sunspot waves in different layers of the solar atmosphere. So we have found that we took one sunspot regions in our analyzed region. We have observed those umbral flash oscillations also, those brightenings we have observed. We have observed those radially propagating umbral waves in the form of intensity disturbances, like some brightenings and dark regions, so bright and dark regions. And we also have observed the coronal waves, the waves intensity waves propagating along the coronal field lines. So we have been able to observe all these three sunspot oscillation and waves in our study. Second, this conclusion, emergence of umbral waves moving radially outward from the location of umbral flashes. So this is still, uh, we are not very sure about the origin of umbral waves. But here in an earlier slide, we showed you. So whenever those flashes were happening, the umbral waves were appearing on both sides of the flashes. So means emergence of umbral waves moving radially outward from the location of umbral flashes. Somehow it says that the umbral flashes, those disturbances may give rise to those radially outward propagating umbral waves. Third, simultaneous amplitude increase in the oscillation of all sunspot waves during the occurrence of the umbral flashes. Most importantly, this is what is our result. So whenever these flashes were happening, almost simultaneous increase in the amplitude of oscillations of these umbral waves and coronal waves. To verify, we have done wavelet analysis, which gives frequency versus time informations, and we have found that there are there are almost increase in the 2.8 minute oscillations, almost simultaneous increase in the 2.8 minute oscillations when the flashes were happening. And we have found finally in this fifth conclusion, significant correlation among chromospheric umbral flash, umbral waves, and coronal waves in cross correlation analysis. We have performed cross correlation analysis, and we have found they are correlated very well. The correlation coefficients we found it to be more than 0.5. And this is the final conclusion, is that this is the first direct observational evidence of the influence of chromospheric umbral flashes on umbral waves and coronal waves. Means this the solar atmosphere is very dynamic. Sometimes though sun is very close to us, we have good signal, but things are very complicated. It's very difficult to do a study from the original light curve without doing any processing. But this is one of the study from the original light curves without doing any processing. We are able to get all those informations, and where we found those umbral flash oscillations, which are some lower atmospheric oscillations, they are affecting the propagation of other sunspot waves happening in different layers of the solar atmosphere. So this is what this study presents. Thank you.
Thank you very much for the very nice talk. Are there already questions in the chat?
No questions so far. I'm not sure because as I was not able to use my pointer, even I was not very comfortable. I don't know whether people have got or not.
No, I think that was not a problem.
Okay, this is like wait.
I guess. Oops.
If anyone has doubt, you can ask you can write in the Google Sheet also. So this is the first research talk, right, in this summer school.
So earlier, Aruberi gave a talk
Okay, today
during
Arubari.
the first week, yeah.
Okay,
And then during this final week, there will be more research talks. So
okay,
yours is the first one this week.
okay, okay. I think they have got a talk in solar physics so far, right? Like the
There
basic.
was only one introductory solar
I think
physics
Nishant
talk.
was, yeah.
Yes, exactly. Yes. This was a nice opportunity for the participants of the school and refresher course to know what is going on beyond IUCAA and beyond NCRA in the different universities in India, especially the ones who are working as associates with IUCAA.
Yes,
So this
yes,
is a good opportunity for the participants to know
yeah, yeah.
what are the applications of the different fields they learned about and
Yes, yes,
where they can find opportunities to work on. So I think this is very interesting.
yes, yes. The most important nowadays is this Aditya is coming and the collaboration. Like I also during my PhD I worked in IUCAA with Durgesh. I was working, so
Right.
most of my work is with him only. So yeah, he's a wonderful person to work with. Like people, if they really want to work, IUCAA is a very good. IUCAA gives a lot of opportunities to people.
Exactly.
So yeah, so that's what I would like to
Yeah.
say to the at this point to the summer school students as well as the associates also. If they want to work, really want to work, IUCAA is always there. So again, and we are also there. So yeah.
Great. Yeah, thanks. So this working with IUCAA associates allows us to reach all the different corners of the country so
Yes.
that they can come and use the different facilities that are available at IUCAA to build contacts with other researchers who are working here and are associated here. So,
Yes.
as IUCAA is an inter-university center, so this is actually the aim of our institute.
Yes. Yes.
All right. So I don't. Do you see? No, I don't see
No, I
any
don't.
questions or
I
any.
also don't see any questions. Okay, then.
All right then. Yeah. So we can